Hey everyone, and welcome to today's Explainer. Today, we're uncovering the invisible physics that literally shape the built environment around us. We walk past these massive structures and rely on them every single day, completely unaware of the gigantic microscopic forces constantly at play right under our noses. So picture this for a second. You're waiting for a train and you look down at the tracks. Or maybe you're driving and you feel that rhythmic thump, thump, thump as your tires roll over a steel bridge. Have you ever actually noticed those small, deliberate gaps? Honestly, it's incredibly easy to look at those spaces and assume they're just, well, construction mistakes, like maybe a slight miscalculation by the builders. But I promise you, they are absolutely not mistakes. It's actually a brilliant piece of engineering. So let's get right into it with Section 1, the mystery of gaps, engineered imperfections. The scientific culprit behind this mystery is something called thermal expansion. It's a pretty straightforward rule. As a solid's temperature rises, its overall size increases. The definition is simple enough, right? But the real-world implications are massive. The sun beats down on a heavy piece of metal, heat transfers into it, and the physical footprint of that object actually expands. Which brings us to Section 2, the science of expansion, zooming into the microscopic world. To truly understand this, we actually have to zoom way, way in, down to the particles themselves. When heat is applied to a solid object, the particles inside absorb that kinetic energy. And because of this newfound energy, they start vibrating, like really vibrating. As they shake faster and push against each other, the average distance between those particles grows, which physically forces the entire solid to expand. It's this perfect chain reaction where invisible kinetic energy turns into a highly visible physical change. All right, moving on to Section 3, linear expansion, stretching out in one dimension. So linear expansion is exactly what it sounds like. It's the increase in the length of a solid when it gets heated up. This specific type of expansion targets long, continuous objects. When that brutal summer sun beats down on miles of overhead electric wires or railway tracks, the expansion is primarily happening in just one dimension. It's stretching out in length. Now, the exact amount of stretch isn't just some random guesswork. It actually comes down to three absolutely crucial factors: the original length of the solid, the exact rise in temperature, and the specific type of material. I mean, steel is going to behave differently than copper, right? Together, these three variables calculate exactly how much extra length engineers have to account for. Next up is Section 4, cubical expansion, expanding across three dimensions. So now we're moving from a 1D stretch to the whole shebang. Cubical expansion is the increase in the total volume of a solid when heated. We're no longer just stretching a wire in one direction. Here, the solid increases across length, width, and height, all at the exact same time. Think about big, bulky industrial objects for a second. Metal blocks, solid steel balls, or massive storage tanks. When these guys heat up, their particles gain that kinetic energy we talked about, causing the entire object to swell outward in literally every single direction at once. Let's put these two side by side to really lock this in. Linear expansion is one-dimensional, an increase in length, just like we see in tracks and wires. Cubical expansion is three-dimensional, a volume increase, like we see in blocks and tanks. And because cubical expansion happens across all three dimensions simultaneously, the overall physical change is fundamentally much greater than what you get with linear expansion. Which leads us to our final part, Section 5, why this matters, preventing everyday disasters. Let's bring this all full circle. Heat causes thermal expansion, period. Linear targets length, cubical targets volume. But here is the real kicker. This is exactly why those expansion gaps are pure engineering genius. Engineers purposely leave these empty spaces in bridges and railways to give the metal room to breathe, so to speak. If they didn't account for this invisible physics, the structures would warp, buckle, and literally destroy themselves under the pressure of their own expanding particles. Crazy, right? So next time you're out and about, take a look around your city. From the concrete sidewalks you're stepping on to the plumbing running hidden through your walls, where else might thermal expansion be secretly at play? The invisible forces of physics are constantly reshaping the macro world around us. You just have to know where to look. Thanks for joining me for this explainer, and keep your eyes peeled out there.